Our speaker today is Charlie White, an assistant professor and extension specialist in soil fertility and nutrient management. Dr. White's extension, research, and teaching focus on the profitable and environmentally safe use of fertilizers and manures in crop production. He also leads programs on how to improve nutrient management through the integration of soil health practices such as cover cropping, reduced tillage, and diverse crop rotations. He has a master's degree in soil science from the University of Maryland and a PhD in soil science from Penn State. There will be time for questions after the presentation, but I think Dr. White may have you respond to questions in the chat box during the presentation as well. Thank you all so much for participating today, and thank you to Dr. White for sharing with us today. If you'd like to go ahead and share your screen, we can go ahead and get started.
Great. Thank you very much for that introduction, Brian. I'm really pleased to be here today to share this presentation with you all and to be partnering with the Pennsylvania 4R Alliance in this initiative to improve nutrient stewardship in Pennsylvania and the broader Mid-Atlantic region. So thanks to you. For you. I appreciate you who are attending today for your interest in this as well and all the work that you do in your jobs to move these concepts forward with the agricultural audience in the region. So today what I want to focus on for this presentation is to talk about the evolution of nitrogen recommendations that we're using in Pennsylvania, talk a little bit about the mass balance approach of where we've been and what we're currently using, but then discuss some new research that myself in collaboration with farmers and graduate students and other researchers and extension agents and industry have been working on to kind of advance beyond those mass balance calculations into techniques that can account for nitrogen supply from cover crops and soil organic matter. So nitrogen has always been a really difficult nutrient to be able to manage for a lot of different reasons. The first of which is that it's a very complex cycle, biological cycle. So on the screen here, we have all of the different processes that convert different forms of nitrogen from one form to another in the soil and in the atmosphere. And it's really driven a lot through microbial activity. And these biological processes, they are dependent on the weather and the soil temperature. There's lots of different pathways through which nitrogen can be lost, for example, leaching or volatilization or denitrification. So, that's a real challenge for us to be able to manage nitrogen efficiently as all of this dynamic cycling that goes on in the soil. Nitrogen is also often the most limiting nutrient for crop yields. Aside from legumes, all of our other non-legumes, grasses and whatnot, tend to respond very heavily to nitrogen fertilizer. And so a lack of nitrogen often might mean a yield decline. Nitrogen is a very expensive input as well to purchase it. And so we don't want to use too much of it because that disrupts the economics of our cropping systems. But we don't want to use too much of it also because it's an environmental pollutant. And so there's the communities that we live in that expect to have clean water and clean air around us in the environment. We need to make sure that from agriculture we're not causing a pollution concern through nitrate leaching or volatilization or denitrification. So all of these things are sort of wrapped up in making nitrogen management a very complex and very important thing that we need to be paying attention to in our cropping systems. So of course, following the 4 R's, which Brian alluded to at the beginning in the introduction, following the 4 R's can improve nitrogen management. So we're talking about the right rate of nitrogen to use. But there's a big question mark around what that right rate is. It's easy to talk about using just the right amount. We don't want to apply too much or it will get lost. We don't want to apply too little or we'll use crop yield. So it's a great concept, but big question marks around what actually is the correct rate to put out. And we have a lot more certainty in understanding what the right forms and the right times and the right placement of nitrogen fertilizers are to reduce losses, but improving our management on the time and placement theoretically should also feed back into what that right rate is. If our nitrogen is being more efficient, shouldn't we be able to use less of it? And currently there's still a lot of questions too about how do those other how do the other 3 R's feed back into what that right rate is. So there's a lot of question marks around what that right rate is. And that's kind of what we're focusing on today, is the past methods and potentially future methods we might use to determine what that right rate is. So determining the right rate also becomes even more challenging when we layer on soil health building practices, which we know are important for both maintaining productivity, but also protecting the environment in terms of reducing erosion and things like that. So practices like no-till and cover crops and building soil organic matter levels, these are important aspects of managing for soil health, but they also feed back into determining what the right rate of fertilizer should be. And currently, we don't have a great way of accounting for this in our recommendations, but we're trying to move forward with ways to be able to account for that. So the agenda for today's presentation is to review the traditional methods of determining recommended nitrogen rates for corn, and then also introduce a new method that we're testing that would account for the nitrogen contribution or potentially even tie up from cover crops, potential contributions of nitrogen from soil organic matter, and also be able to accommodate the economics of nitrogen fertilizer based on fertilizer prices and corn grain prices, using those to adaptively adjust your fertilizer rate. So just to give some background on the traditional mass balance approach to determining nitrogen recommendations, we have this old rule of thumb of using 1 pound of nitrogen per bushel of expected corn yield. And so where did this rule of thumb come from? What I'm showing you here is a figure that represents about 50 different nitrogen response trials in corn that were conducted around the state of Pennsylvania. Many of them were on-farm experiments. And each of these bars here indicates an experiment, one experiment that was conducted at a location where different rates of nitrogen fertilizer were progressively added to corn. And then they measured the yield response. And these studies were done sometime in the 1990s, just to give you a sense of the era of this data. So from that nitrogen response, we can calculate the economic optimum nitrogen rate, which is the rate of nitrogen where the yield increase is no longer gives you an increased economic return compared to the price of the next additional pound of nitrogen required. And so then each of these bars is then sorted across the x-axis here from the lowest corn yields to the highest corn yields that were achieved at the optimum N rate. And so these sites also have no previous manure history and no previous legume credit. So how is this data used to generate our 1 pound of N per bushel of expected yield? We might expect to see that these economic nitrogen rates should be increasing progressively and consistently as our corn yields increase, and they really don't follow that pattern. Instead, where our 1 pound of N per bushel of expected yield comes from is that these are recommendations designed to bracket the maximum required nitrogen across, say, 95% of the scenarios. And so if we categorize our corn production into certain categories from 130 bushels per acre and below, from 130 to 160, 160 to 190, and 190 to 220, if we use a rule of thumb of 1 pound of N per bushel of corn produced, 130 bushels of corn would require 130 pounds of N. And notice that line brackets the maximum required within that category. 160 pounds of N brackets almost, with 95% certainty, the maximum required. 190 brackets the maximum required. So really, this is a very conservative recommendation philosophy here that most of the time is actually more than enough. So all of these experiments that were below the line here in this category, we're actually, if we followed this recommendation, we'd be over fertilizing, and that's not good for the environment. It's also not good for economics. But these recommendations are designed to protect against yield losses from under-fertilization. Now, we also have credits that we can take that would reduce the nitrogen fertilizer required based on previous legumes in rotation. So we have tables in the agronomy guide that provide a credit to a previous alfalfa or clover trefoil hay crop or previous soybean crop. And you would subtract off that nitrogen fertilizer based on what these previous crops in rotation would provide. We have similar tables with previous manure applications over the last 5 years. You count up the number of years out of the last 5 that manure was applied. That gives you a certain frequency category. And from that frequency category, you take a certain nitrogen credit that you subtract from that 1 pound N per bushel. So that's kind of the mass balance approach. We have these requirements minus the credits gets us at a recommendation. Now, there's also more adaptive approaches that historically have been used. One of the most well-known is the pre-sidedress soil nitrate test. The idea with this test is that during the growing season of corn, when it's about 12 inches tall, we take a soil sample to 12 inches deep and we send it to a lab and measure the nitrate concentration in the soil. And the nitrate concentration is an indicator of how much nitrogen is becoming available for mineralization of soil organic matter. And that soil organic matter might be from previous crop residues like legumes, it might be from previous manure history. And if the soil nitrate level is over 21 parts per million, it's a very accurate determination that no additional sidedress N is required. I should mention that this test is designed to be used with only a fairly small amount of nitrogen applied at planting. So maybe 25 to 50 pounds maximum nitrogen applied at planting. The goal is not to measure how much nitrogen is left from your at planting application. It's designed to measure how much is being generated through mineralization of organic matter. So we don't want to skew the signal of that soil mineralization by applying lots of fertilizer up front, because when we come back and measure it, in June, we're mostly just measuring the fertilizer we applied, not the soil mineralization. Now, if the soil nitrate is less than 21 parts per million, we can use this value as a more accurate way to account for previous manure history and legume nitrogen credits and determine a sidedress nitrogen rate. So below is an example of the formula that is used to convert soil nitrate into a fertilizer recommendation. And this is published in Agronomy Facts number 17. It's also in the agronomy guide in the corn chapter. And the way this formula works is you start with the soil nitrate level, then you have what your expected crop yield is, and then you have to calculate what's called the history factor. And the history factor takes into account the amount of manure that's been applied to the field since the last harvest, the previous crop in terms of whether that was corn, soybeans, or a forage legume, or something else, and then a manure history of whether manure has been applied in the past 3 years. These history factors are all added up to create this coefficient called the history factor here. Now, to determine the fertilizer recommendation, what we start with is the yield factor, and then we subtract off the history factor times the soil nitrate level. So there's a couple key things here about this formula that you need to be aware of. First of all, the fertilizer recommendation will never be greater than the expected crop yield. And notice this yield factor is basically the crop yield times 1 pound N per bushel. So we're never going to have a greater fertilizer recommendation for side dressing than the yield factor. And the other thing to notice is that what the soil nitrate subtracts off in terms of its quantity is dependent on your history factor. And this is what I call a calibration of this test. This test is calibrated such that the meaning of a 1 part per million of soil nitrate is dependent on previous manure histories, previous crops in rotation, and any manure applied since the last harvest. So the context really matters in determining what the final result is in terms of the sidedress recommendation. Now, one of the challenges with the pre-sidedress soil nitrate test, and again, just like our mass balance recommendation of 1 pound N per bushel, the data was mostly generated in the 1990s. So it is very old data that went into calibrating this. Notice that our history factors don't have anything about cover crops in them, whether it was a previous legume cover crop or a grass cover crop. It doesn't have anything about whether the field is no tillage or not. And most of the studies that were done to calibrate this were conducted under tilled conditions. And tillage will speed up the mineralization process. It aerates the soil, it warms the soil, it stimulates microbial activity. And so you're going to have a different trajectory of soil nitrate mineralization in a tilled system versus a no-tilled system. But we currently don't have a history factor to account for that. In terms of cover crops, over here shows you a figure of what soil nitrate levels look like over time under different cover crop treatments in the soil. And the PSNT is calibrated for a measurement that's taken in June to be able to predict what's going to happen in terms of mineralization in the future. And we currently don't know what a part per million of nitrate means under a pea cover crop versus a part per million of nitrate under a grass cover crop like triticale or rye. And so we haven't calibrated this test. So I think it's important to recognize that if you are using this test in no-till systems or cover crop systems, you're really pushing it beyond the conditions and the context under which it was calibrated. And I think you need to be a little bit more hesitant and skeptical in using those results outside of the context in which it's calibrated. So just to summarize our basic mass balance approach, the traditional N recommendations of a pound per bushel are too often excessive, yet sometimes they're not enough. So sometimes we actually required more nitrogen than would have been predicted by our 1 pound per bushel rule. And in my opinion and in my experience, the not enough situations of our recommendations providing not enough are going to be more common when we start having cover crops that are immobilizing nitrogen and tying up nitrogen as they decompose. And so the question is, how do we move forward in the modern era with a new nitrogen recommendation system that can account for the effects of soil organic matter and cover cropping practices that might be expected to change nitrogen requirements for our corn crops? So what I want to look at here are two response curves that we collected from experiments that were conducted in 2020. And if anyone was around central Pennsylvania in 2020 and remembers what the cropping season was like, we had a severe drought. And so this is a yield response curve where we increased rates of nitrogen to corn, and then we saw the yields topped off at about 115 bushels of corn. So we only produced 115 bushels of corn. And under the, typically we'd be producing 150 to 180 on these soil types in this climate. And we see that the nitrogen fertilizer at the economic optimum rate based on the price of fertilizer in 2020, which was about 30 cents a pound, and the price of corn in 2020, which was about $4 a bushel, the economic N rate would have been 173 pounds of N to produce only 113 bushel of corn. Okay, so that definitely does not fit with our 1 pound N per bushel, right? We would have, if we use that rule, we'd only be applying 113 pounds of N in this scenario. Now, another farm in 2020 in Lebanon County, which was only slightly drier than normal, yields were a little bit off, but still quite good, 214 bushel of corn. And notice that in this scenario, it only took 172 pounds of N to produce 214 bushel of corn. So very different yield goals in these two scenarios, yet the same amount of N was required to reach these very different yields. So that kind of violates our current mass balance approach that assumes, the nitrogen requirement is tied to the yield goal. What I want to ask you to do is look at these response curves, and what is it about the response curves? What could you maybe extract from these two response curves that is the same between them that might be controlling what this nitrogen requirement is? What component of these response curves, if you sort of dissected it and pulled it apart and maybe calculated something new from within this response curve, what would be the same about them? And I want you to take a minute to chat in your ideas about what's the same of these two response curves. So we'll just take 30 seconds, pause for folks to look at that and chat in some ideas. All right, great. We have someone suggested the slopes were the same. Someone also asked about the soil type. The soil type was actually somewhat different between these experiments, so it's not the soil type that's the same. It is something that's kind of related to the slope of these curves. So notice they've both got a similar type of slope from between their yield at N0 and their maximum yield and their N required. And what I like to look at in these is I call it the yield gap. And so this is sort of a component of the slope, right? For the slope, we talk about how much does the line rise versus how much it runs across. In terms of this, both of these response curves have a 40 bushel per acre yield gap from their yield at N0, zero fertilizer applied, to their maximum yield. There's both a 40 bushel per acre difference there. And one of the things we're seeing with data that we're analyzing is that this yield gap is very predictive of what the nitrogen requirement is. So the fact that these two fields had the same yield gap, that's kind of what's driving them to have the same N requirement. I appreciate all the other ideas that were chatted in here. Ben mentioned that the data is spread very widely, and yes, that is. This also was a field with kind of highly variable soil types, and so as we got to different pockets of soil, some held water better than others. We had some very sandy patches within this field, and certainly that would stress the crop more or less. Yeah, and they're both experiments. The corn yields respond with marginal increase in yield compared to each additional increase in N. That's very typical of crop response curves. Yep, very good. All right, thanks I appreciate those observations that folks made in the chat here. Okay, so I want to show two other response curves from other sites. Here's one in Berks County. This was from 2020. We had a mature wheat cover crop, and we were able to grow about 250 bushel corn. We did get, I would say, probably optimum levels of moisture in this at this site in this year, but it took 275 pounds of N to get that 250 bushel of corn. And this is a site that had a mature wheat cover crop, and that wheat cover crop was immobilizing lots of nitrogen as it was breaking down. And notice how steeply the yield drops off as the N rate declines. So this is actually a site that responded fairly efficiently to increases in nitrogen fertilizer, up until the very end. Now, another site that we harvested earlier this year in Lancaster County, we grew almost the same yield goal or yield potential, 241 bushels of corn, but it only took 134 pounds of N to get there. And again, we have a much smaller nitrogen yield gap here between our N0 and our maximum yield. And so it required less nitrogen to get there. This site also had a very young rye cover crop that was killed early. And so that rye cover crop actually was able to mineralize nitrogen back to the soil. So here we see 175 bushel per acre yield gap versus a 30 bushel per acre yield gap. That's really what's driving this nitrogen requirement. It's not much at all having to do with what the overall yield goal is, 241 versus 250, relatively similar overall yield goals. It has to do with the yield gap. So we've looked at this extensively from corn nitrogen response trials in the mid-Atlantic states as well as all over the nation. This is a figure that a postdoc in my group assembled from mid-Atlantic states, and it shows you the yield gap, which is the difference between the yield at N0 and the maximum yield, versus the pounds of N required per bushel of the yield gap. So if we take the N requirement, divide it by the yield gap itself, that gives us pounds N required per bushel of yield gap. And we see there's a relatively tight relationship here, and as the yield gap increases, we need less pounds of N per bushel of the yield gap. But how do we use this data to determine an overall N rate for a field? What we actually have to do is multiply the yield gap by the pounds N required per bushel of yield gap. So for example, a yield gap of 150 bushel per acres requires 1.6 pounds of N per bushel of that yield gap, or 240 pounds of N per acre. As our yield gap declines, the N required per bushel of yield gap starts to go up, but when we multiply them together, we see our overall N rate starts to decline as our yield gap gets smaller. So a 50 bushel per acre yield gap only requires 140 pounds of N, and a 25 bushel per acre yield gap requires 125 pounds of N. So this is a relationship that we can use if we can understand in different scenarios what the yield gap is. We can understand what the nitrogen requirement is from this relationship. So the question is, how do we predict what the yield gap is? The yield gap is essentially the maximum attainable yield, so minus the yield with 0 N fertilizer applied. So the maximum attainable yield, this is going to be something that is driven by the climate, the soil type, potentially corn varieties, and the management skill of the farmer. This is probably going to vary from year to year within reasonable bounds based on the growing season, whether we get enough rain or not enough rain. But, it varies within reasonable bounds. And I think farms that are the 300 bushel producers, they know who they are. Farms that are the 150 bushel producers, they know who they are based on their previous experience. And someone's not all of a sudden going to switch on the same farm from being a 150 bushel producer to a 300 bushel producer. Okay, we just don't see swings that wild from year to year. So it's going to vary, but within reasonable bounds. So we can probably determine more or less what the maximum attainable yield is based on previous experience from our site. Now, the yield with 0 N fertilizer applied, this is highly dependent on the soil N supply. It's controlled by microbial mineralization and immobilization during the decomposition of soil organic matter and cover crop residues. It will depend to some extent on the climate, the soil texture, the organic matter level, and the cover crop nitrogen and C to N ratio. And the question is this predictable? And this is a question that my research group has been asking for a number of years now. And it is something that we do think we can predict with some basic agronomic measurements of the soils and the cover crops. And that's what I want to talk about now. So to predict this, we need to be able to understand the nitrogen mineralization process, because that's at the yield of with no fertilizer added. That's what we're relying on. We're relying on microbial mineralization of nitrogen. So in this process, microbes are decomposing carbon. That carbon might be soil organic matter, it might be cover crop residues. The microbes are using some amount of that carbon to build their biomass. The rest of the carbon is respired into the atmosphere as carbon dioxide. Now, as the microbes are breaking down carbon in this organic matter, they're also breaking down a certain amount of nitrogen based on the ratio of carbon to nitrogen in that residue. And if there's more nitrogen in the residue, more nitrogen will break down with every unit of carbon that's broken down. More nitrogen in the residue means we have a lower C to N ratio. Now, microbes, as they're building their biomass with carbon, need some amount of nitrogen to build their proteins and amino acids and cell walls and things like that. What's left over from what breaks down and the microbes don't need to build their biomass, what's left over is what's mineralized in the soil as ammonium. And that's what the crop can utilize, and that's what the yield of unfertilized corn will respond to. It will respond to this amount of ammonium that's mineralized into the soil. Now, this is somewhat of a complex biological process, but there's actually components of the process that we can break down into an equation. And this equation predicts the nitrogen that's mineralized based on the total nitrogen in the cover crop, the C to N ratio of the cover crop, the efficiency with which microbes utilize carbon versus respire it to the atmosphere, and then the C to N ratio of the microbial biomass. So we can predict, if we know some of these parameters, we can predict the amount of nitrogen and how the corn yield will respond to that. So looking at different cover crop C to N ratios, on this spectrum, we have low C to N ratios, mean we have a high nitrogen concentration. On this side of the spectrum, we have high C to N ratios, means a low nitrogen concentration. And at some point, we shift from having excess N that mineralizes during decomposition, we shift to, as the C to N ratio goes up, at some point we shift to what we call immobilization, or tying up nitrogen from soil. The microbes basically don't have enough nitrogen in the residues they're decomposing, so they tie it up from available pools in the soil. And this would cause corn yield to decline. This would cause unfertilized corn yields to increase. So different cover crop types have different C to N ratios. Legumes like clovers and peas tend to have a low C to N ratio and tend to mineralize nitrogen. Radishes are kind of moderate. Canola, depending on how late you let it grow, will get more and more woody and stemmy and have a higher C to N ratio. Same for all of the other cereal grasses and non-legumes. If you kill them early, they have a low C to N ratio. If you let them get really mature, they have a high C to N ratio. And at some point, they'll shift from being nitrogen suppliers to being nitrogen, causing nitrogen tie-up. So when we look at the effect of the cover crop C to N ratio on corn yield responses, this is data that shows corn silage yield from an experiment where we grew different cover crop types. So we have a pea and a clover, we have a fallow, we have different mixes of cover crop species. This is corn that all received the phosphorus rate of dairy manure and no other nitrogen fertilizer. And this red dotted line is drawn at the level of the no cover crop control here. And what we see is that as the cover crop C to N ratio gets higher and higher, the corn yield starts to decline. And the C to N ratio is getting higher because our mixes have more and more cereal rye in the seed blend up to the pure rye monoculture had the highest C to N ratio. Now, on the other side of the spectrum, we have clovers, a radish, and a pea, where the C to N ratios are relatively low, and we see that the corn yield is increasing because of those low C to N ratios due to the nitrogen supply there. So one of the other components that's important is the total quantity of nitrogen in the cover crop biomass, in addition to the C to N ratio, and that's an important component of our experimental recommendation system. And you might wonder, how do we get that nitrogen content of the cover crop stand? Well, one of the things we've tested and developed is using this tool called the Green Seeker. It's a handheld tool that measures the reflectance of red and near infrared light on the crop canopy. You can also get this NDVI data from satellite imagery. This is a handheld sensor, but these sensors can also be mounted on spray booms, and they can map the cover crops as you're going across the field. But we've determined that there is a fairly strong relationship between the NDVI, measured by one of these sensors, and the nitrogen content of the cover crop. As the nitrogen content goes up, the NDVI goes up. So this is a sensor that you could use. This is some videos of a technician and grad student in my group walking the sensor across a field, and you can see what the number looks like here. That 0.64 is the NDVI number, and we can look that number up on a chart to indicate what the total nitrogen content is of this cover crop stand. It depends a little bit on what type of cover crop is. The calibration is slightly different, but we have all of that information available. So the other component that we have is we've developed calibrated equations that predict what the unfertilized yield will be based on cover crops and soil organic matter. And these sets of equations require some testing to be done, some soil sampling and some cover crop sampling to be done. But first thing we do is we use the sand content of the soil to calculate a parameter called the humification efficiency. And this is essentially how efficient are microbes at using carbon, building it into their biomass. We measure the soil carbon percentage or the soil organic matter percentage that's multiplied by the humification efficiency term, and that predicts the corn yield response to mineralization from soil organic matter. We have a component where we measure the nitrogen content in the cover crop biomass and the C to N ratio of the cover crop biomass. And notice this humification efficiency term that's controlled by the sand content is factored in there as well. And ultimately, and that predicts the yield response to nitrogen mineralization from cover crop residues. And sometimes this value is positive if something is mineralizing. Sometimes this value is negative if something is immobilizing. We then add these two things together and adjust it with some quadratic curvature here to get a total unfertilized corn yield based on nitrogen mineralization from soil organic matter and cover crops. And we've calibrated these formulas, these values, the 0.77, the 9.85, the 0.026. These aren't just random values that I pulled out of a hat. These are mathematically calibrated values based on real field experiments in Pennsylvania. And we've been able to predict with a decent level of accuracy what the unfertilized corn grain yield will be for a given site based on measurements of soil organic matter, soil texture, and cover crop nitrogen and C/N ratio. So those equations are now being used in the background of an experimental tool to credit nitrogen availability from cover crops and soil organic matter. What we do is predict the yield that can be achieved on nitrogen mineralization alone. We know from previous experience what the yield goal might be based on the climate, soils, and management. And that difference is the yield gap, and we can use that yield gap to predict the nitrogen fertilizer requirement. What this framework allows us to do is adjust our nitrogen recommendations based on whether we have no cover crop growing, a legume cover crop that might mineralize nitrogen and increase unfertilized yield would have a lower fertilizer requirement. A rye cover crop that might immobilize nitrogen and increase the yield gap would have a higher nitrogen requirement. This would also change based on soil organic matter and on soil texture as well. So it's a very flexible and adaptive framework for calculating a nitrogen fertilizer requirement. There is a tool that's currently online. I call it version 1 of this tool. We have had additional research that has gone into improving this tool, and so there's a version 2, which we're hoping to release as soon as we can, once we've done some additional on-farm testing to make sure that it's, verified that it works correctly. But what I'd like to do now is give you a quick demo of what the version 2 decision support tool looks like. So I'm going to shift screens to my web browser here and show you what that tool looks like. All right, I think everyone can still see my screen. So this is what the tool looks like. On the left side here, we have inputs of your corn yield goal, your sand content, your soil organic matter level, and then information about the cover crop biomass nitrogen content, the C/N ratio, the price of corn, and the cost of nitrogen. In terms of using that green seeker sensor down here, there is a tool where you can choose the cover crop type that you're measuring, and then you can type in your NDVI value from the green seeker sensor, and it tells you what the conversion is to the cover crop biomass nitrogen. So, as I mentioned, this depends a little bit on the type of cover crop that you're measuring. So you can choose that from this drop-down box here. So looking back up at the tool, the first thing you would want to do would be to dial in your corn yield goal, and that determines kind of the maximum yield that can be achieved at a site based on the climate and the soils and the management, and that controls to some extent your nitrogen yield gap. We can dial in the sand content, and that controls the mineralization rates. Basically, as we increase the amount of sand, nitrogen will mineralize at a faster rate. That's going to increase our unfertilized corn yield. So down here, as I move these inputs around, you can see that this yield response curve is changing. Our yield at N0 here will change based on soil mineralization rates. As we increase or decrease our soil organic matter level, again, we see that our unfertilized corn yield changes. That changes our yield gap, which changes our N fertilizer requirement. We can dial in different levels of cover crop residue nitrogen. So we could compare, say, a pure legume with a C/N ratio of 10 versus mature cereal rye with the C/N ratio of 35, and see how that might change our nitrogen requirement. We could look at, say, whether you grow a small cover crop with a little amount of nitrogen or a big cover crop with a lot of amount of nitrogen. So you can also use this tool to do some scenario testing to see what the benefit might be of letting a cover crop grow bigger, or maybe if it's a grass cover crop, killing it earlier. And then the other thing that we can do now that we have a prediction of what the yield response curve might look like, is we can now enter in economics into the decision making as well. And so we can look at the price of corn and the price of nitrogen. And typically, as the price of corn goes up, it pays to fertilize with a little bit higher rate. So if I increase this from 585 to, say, 650 or something like that, we should see the optimum N rate increase a little bit. So I'll type 650 in here, and it went from 109 to 114 pounds of N. So relatively modest shift in what the fertilizer requirement might be. If we reduce the cost of nitrogen to something more typical of what we've experienced in previous years compared to this year, we can see that that has a really big impact on how much nitrogen is required. Now, this economic component will certainly have a bigger effect when your response curve is relatively flat compared to when it's really steep. So if I were to say, draw down the soil texture here and draw down the organic matter a little bit here, now our corn yield response is very steep, and the economics actually have relatively much more of a minor effect on how those rates change. So that's just a quick example of how this tool works. I'd be happy to share this with folks, and in fact, maybe when we get to a break here and have some questions, I'll post this file. This is just an HTML file that you can look at through a web browser. I'll post that into the chat if folks want to play around with this and try it out. So let's go back to the presentation here and look at maybe how this tool compared to some of our current mass balance or adaptive approaches. So this is the experimental site from Lebanon County in 2020 when things were slightly drier than normal. There was a 215 bushel per acre yield goal, and we know this from after the fact. So this is kind of a post-mortem analysis. There was a previous soybean crop that produced 50 bushels per acre. Frequent manure history, basically this farmer applies manure, typically would apply manure in the corn years, and he's got a corn-soy rotation, so only about half the time is this field getting manured. There was no cover crop. From soil tests, we measured 21% sand, 7.7% organic matter. The PSNT test in June was 18 parts per million nitrate N. Now, the agronomy guide mass balance N recommendation would be 215 pounds of N, which is 1 pound of N per bushel of yield goal, minus the 50-pound soybean credit, minus the 20-pound manure credit, would be 145 pounds of N would be required here. What we actually saw from our response curve is that the economic optimum in this year was about 172 pounds of N. So we'd be shorting our crop about 30 pounds of N approximately by following the mass balance approach. So this is a scenario where the mass balance was not enough, actually. If we use the PSNT side-dress N recommendation, 18 parts per million, accounting for our various history factors and our yield factor, would have suggested applying 152 pounds per acre side-dressed. Now, we had already applied 54 pounds N per acre at planting, and so the total N applied during the year, which is what we have on the x-axis of our experimental data here, the total N applied would have been 206 pounds N. So 206 pounds of N would have put us kind of right here. It would have maximized the yield. We would have probably gotten maybe a bushel or so more, but it would not have actually been a profitable application of that extra fertilizer. We basically wouldn't have recouped any of that additional cost. The economic optimum in this year was 172 pounds of N. Now, when we look at our experimental decision support tool and we put all of those inputs in, and in 2020, the price of corn was $4 and the cost of nitrogen was 30 cents a pound, the tool was suggesting that we apply 164 pounds of N total, and the experimental data suggested 172. So that's pretty darn close, I think, within the realm of error and variability and calibrating equipment and things like that. I think this tool, was behaving very well in this scenario and was giving us a recommendation that was closer to the true value than either of the other two tools that we looked at, the mass balance approach or the PSNT test. Now, a question you might be wondering, that was 2020 corn and nitrogen prices. What would the tool suggest in the current price environment? And previously, we were looking at 164 pounds of N. Just this morning, I ran this for 2020 corn and nitrogen prices, where the price of corn with the local basis of $5.85 a bushel and cost of nitrogen at the retail level around 90 cents a pound. And based on the economics of that, our tool is suggesting a rate of only 149 pounds N per acre. So basically, reduce N fertilizer by 15 pounds per acre compared to 2020. And the result of that is actually only losing 1 bushel per acre of grain yield. So, you know, you're saving almost $15 and you're only losing 1 bushel of corn. So in the end, you're winning out economically by making that reduction in fertilizer application there. So another site from 2020, Berks County, where we had the mature wheat cover crop. Again, pumpkins was the previous crop. It had a frequent manure history, a mature wheat cover crop with a high C to N ratio, very low amount of sand, which will reduce nitrogen mineralization with this low level of sand, relatively low organic matter level, PSNT value of very low, 5 parts per million nitrate. And you can see how steep this response curve is. We required 275 pounds of N, which includes some credit for a fall manure application to reach 250 bushels. When we look at the agronomy guide mass balance approach, it would recommend, based on the previous manure credit and available nitrogen in fall poultry manure, a fertilizer recommendation of only 158 pounds N per acre. We actually required 246 pounds N per acre, and then we're crediting about 29 pounds from fall manure, and that gets us to our optimum. So again, this is another case where the mass balance approach was not enough, and it was off by quite a bit. 158 pounds of N fertilizer required would put you kind of right here, losing, you know, almost 50 bushels of corn yield following this recommendation. Based on the PSNT actually gave a much closer side dress recommendation of 224 pounds per acre. The correct side dress N recommendation was 213 pounds of N per acre, which, you know, that the side dress rate is not indicated necessarily right here. This is the available nitrogen from the fall manure plus the app planting plus the side dress. The correct side dress rate would have been 213 pounds. So the PSNT test actually did a pretty good job in this case of predicting the nitrogen requirement. But again, our tool, putting these values into the tool, you see the shape of the response curve that's predicted is very similar to the shape of the response curve that was experimentally determined. You see that the cover crop impact actually was reducing the unfertilized corn yield by 92 bushels per acre. So this is a great example of where maybe this farmer shouldn't have let this wheat cover crop grow to the point of having heads emerged and immobilizing a lot of nitrogen. So you could do some scenario playing with this around whether you kill your cover crop early or late. If we had been able to pull this C to N ratio down a bit, I think he wouldn't have needed quite as much fertilizer here. Again, in the 2020 price climate, 279 pounds of N recommended in total, and we see 275 pounds of available N experimentally determined as the optimal N rate. So again, very close between our tool and our experimental observation. Looking at this site in the 2022 corn and nitrogen price climate, actually, even though it's a very different response shape of the response curve, the outcome was actually exactly the same in terms of how much to reduce your N fertilizer by. It was a reduction in 15 pounds per acre, and the impact was only a 1 bushel per acre loss in grain yield. So I think this is kind of helpful, and actually a lot of the scenarios I've looked at from our experimental data comparing 2020 to 2022, I'm seeing very consistently between 15 to 20 pounds per acre reductions being called for based on the profitability side of things. So I think that might be something helpful for those of you that are working with farmers and trying to make suggestions about how to navigate the high fertilizer prices. Seems to be pretty stable result from a lot of different locations that reducing 15 to 20 pounds per acre is a profitable move to make in the current price climate. So to conclude here, the mass balance nitrogen recommendations, they've always been a very crude approach to try and determine what the nitrogen fertilizer requirements are. They, in the past, have tended to be provide more than enough, but we're seeing with growing big cover crops that potentially immobilize nitrogen, we're seeing more and more scenarios where these mass balance approaches are not enough. This mass balance approach is not set up really well to handle nitrogen credits or deficits from cover crops and changes in soil organic matter or changes in economics. In-season adaptive tools like the PSNT test may need some additional calibration to account for no-till and cover crops. We are doing research to see whether we can create some additional history factors for that based on these factors. But I'm really pleased with how our decision support tool is working to predict the nitrogen requirement for corn following cover crops and being able to adjust for things like different species of cover crops with different N content and C to N ratios, soil texture, soil organic matter, and the economics of fertilizer prices and corn prices. So there's a lot of funding agencies and that have contributed work towards this research. There's a lot of collaborating farmers that have contributed their fields and their management time and resources to doing this research. A lot of students and technicians and postdocs and extension partnerships have gone into this. So I'm very appreciative to all of those people. I do welcome you to contact me if you have an interest in this, my email address or my telephone number. Send me a message or give me a call, and I'll be glad to talk to you about this further. So I think at this point, I'll stop talking and see if we have any questions or discussion from the group.
It looks like Eric had a question in the chat there.
Yeah, exactly. So the placement of nitrogen fertilizer. So that's a great question, and that is sort of an advanced level of work that currently we aren't able to accommodate. I will say that our trials here that have led us to this calibration have all been where the majority of nitrogen is being side dressed. So we have improved timing. We're side dressing it in bands, oftentimes with fertilizer that has urease and nitrification inhibitors in it. So we're using stabilizers. So I'd say we're using a suite of best management practices to generate this data. So maybe an assumption that's kind of built into our response curves here is that you are using some of these best 4R practices. And so I'd say if you're not using those practices, then maybe our fertilizer recommendations might not be quite adequate enough if you're experiencing a lot of losses. For example, say broadcasting urea on the soil surface at the very beginning of the cropping season and having lots of volatilization losses, you might come up a little bit short compared to what our tool is recommending. I saw another question in here about, can you explain again how sand content affects N mineralization? Yeah, this is a great question. And it's one of the really interesting things that has come out of our research is the relatively high importance of sand content. Essentially what sand does, and it's not so much what sand does, it's actually what the inverse component of soil texture does, being the clay content. What clay really does is clay has a very high surface area, so very small particles with high surface area. That surface area actually is highly attractive to organic matter, and it protects and stabilizes that organic matter against microbial attacks. So the more clay content you have in the soil, the more protected your organic matter is, and the less that organic matter will be accessible to microbes to kind of mineralize. The more sand content you have, the more free and available your organic matter in the soil tends to be for microbial attack. And so the microbes can kind of, can really feast at it and mineralize a lot of nitrogen in a very sandy soil. So that's kind of how it works. Yeah.